Guys, so we're going to go ahead and take a look at our Unit 1 review. This is what your review will look like, at the end. So you want to make sure that you have at least 4 different colored pens or 4 different colored pencils because we have a lot of work that's going on. As you can see, this is what yours should kind of look like towards the end. So for Unit 1 review, this is just a reminder of what we did today. So today, we looked at the amount of enzyme concentration to see how much the chip broke down. That was our DV. And we spit at different volumes. Our control group was water because our saliva has 99% water. Tomorrow, we're going to go ahead and add ice to our saliva so we can retard the breakdown of amylase. I think that at regular temperature, that it just happened to break down due to it being maybe too hot, like it was denaturing. We're also going to go ahead and add heat so that we can go ahead and accelerate the reaction, and we'll get to see how temperature has effects on amylase. So this is what we're going to do. We're going to review the top diagrams for you to know, but that doesn't mean that's everything you need to know. I would advise that you label them, put them on note cards, test your partner. This is not mandatory, but this has helped students in the past. And just make sure that you're reviewing your Cornell notes. So number 1 is the metabolic pathway. If, for example, so this is our metabolic pathway, if we take out enzyme 1, then B won't be able to be made. And if B isn't made, then C won't be made. And if C isn't made, then D won't be made. So this is a metabolic pathway. If we shut down one of the enzymes, the rest of the pathway will not work. Our next diagram that we have is an energy graph with an enzyme. So first we're going to take a look at our axes. This axis represents free energy, while this one represents the progress of the reaction. This area right here that is purple represents the free energy in reactants. If we follow this black line, which is the original one, it goes all the way down to products. This area right here represents the energy for products. Now if we add a catalyst, we can see that we have a smaller little hump. So this area underneath the hump is the activation energy. When we have an enzyme, it lowers the activation energy, which causes the reaction to go faster. But you need to know that this doesn't change the amount of reactants, this doesn't change the amount of products, it doesn't change the amount of energy that reactants have, and it doesn't change the amount of energy that products have. This area right here between our activation energy, or in other words, our reactant energy, and our products is considered delta G. This is also not affected by the enzymes. This would be considered to have a negative delta G, so therefore this would be considered exergonic. Our third diagram you need to know is an enzyme graph. So we have temperature on our x-axis and rate of reaction on our y-axis. The higher that we are on the y-axis, the higher the rate of reaction that we have. So for example, at these 2 peaks, we have the highest activity. But here's the thing. If we're looking at this human enzyme, anything over, let's say around like 50 degrees Celsius would definitely cause the enzyme to not work. This is most likely from the enzyme being denatured. If I look at this bacteria, anything over 90 degrees Celsius is going to cause it to not work at all. There's 0 rate of reaction, which probably means the enzyme has been denatured. This is our 4th diagram. So this 4th diagram deals with calculating rate. Rate is rise over run, or it's y2 minus y1 over x2 minus x1. So let's calculate the rate from 10 to 20 seconds. So we're going to have 20 minus 10 on the bottom, and then on the top, okay, let me fix this. Okay, there we go. So 20 minus 10 on the bottom. On the top, it should be 0.27 minus, here's 10, 0.37. That's going to equal negative 0.01. So please just make sure that you know how to calculate rate. You'll be expected to do this. This is a skill you must master. Now I'm going over hydrogen bonding because on a reading quiz, a lot of people got this wrong. One of the questions was asking about hydrogen bonding, and some people put that it's between the same water molecules. This is not true. Hydrogen bonding is actually between different water molecules. So for example, this is a water molecule, this is another one. It is hydrogen bonding to a different water molecule. That doesn't mean that they're not both water. It's just that in order to have a hydrogen bond, it takes at least two. So it takes two to tango, or two to hydro, or however you want to say it. The positive side is attracted to the negative side, or in other words, the positive hydrogen is attracted to the negative oxygen. And these are between, again, different water molecules. Oh my. Let's keep going. So now we need to go over dehydration synthesis, and then we need to go over hydrolysis. For dehydration synthesis, let's break down these words. This is losing water, where synthesis means building. Hydrolysis, though, means adding water and breaking. So in this diagram of dehydration synthesis, it is producing water, and it's making a monomer add onto a polymer. Versus breaking for hydrolysis, we're adding water, and this is going to cause a monomer to separate from a polymer. Let's go ahead and go on to the next one. Now we have a lot of things we need to talk about, and this is going to go kind of fast. We need to talk about bonds, and we need to talk about biomolecules altogether. So this first one is a protein, and this is 2 amino acids that are going to be bonded together. This is done through a dehydration synthesis, and the bond between them is called a peptide bond. The molecules involved are carbons, hydrogens, oxygen, and nitrogen, or CHON. The way that the peptide bond forms is important. You get a hydroxyl from the carboxyl group and a hydro from the nitro. So hydroxyl from the carboxyl, hydro from the nitro. Those will make water, and then you have a peptide bond. The next thing that we have is carbohydrates. These are when you have 2 monosaccharides and they form a polysaccharide through dehydration synthesis. The bond that they create is a glycosidic bond. The molecules that are involved in carbohydrates are carbon, hydrogen, and oxygen. Next we have a lipid. Lipids are made of fatty acids and glycerol, and they're held together by a very strong woman named Esther. These are made of carbons, hydrogens, and oxygens. Our next one that we have is a nucleic acid. This looks like an RNA. Nucleic acids are made out of nucleotides, and they have phosphodiester bonds that help hold the sugar phosphate backbone. So here's our phosphate, and our diester are these 2 oxygens over here. These do have hydrogen bonds that hold the bases together. However, it can't be seen in this diagram. This is made out of carbon, hydrogen, oxygen, nitrogen, and phosphate. Next, we have an enzyme graph. So this is number 9. On the enzyme graph, what you can see is this area is starting to increase quickly. That's because the enzyme is consuming the substrate. The more products that we have, so for example, this is the amount of product, that means that it came from more substrate. If I have more substrate, I'll have more product, and my reaction will actually go faster. Over here, you can start to see that it actually starts to slow down, and it kind of looks like it's starting to go constant. This is due to the enzyme consuming all of the substrate. At some point, if you put a set amount, it should consume all of the substrate. The last one that we have is number 10. Now, number 10 has 3 types of enzymes in this graph. But I want to make one thing clear. You need to make sure that you understand what is considered acidic and what is considered basic in this graph. So for example, acidic is going to be like, for example, like 1 through 5, or 1 through 6, whereas neutral will be 7, and then basic will be 8 through 12. So let's go ahead and take a look at all of these. We have pepsin right here, and pepsin is showing high activity at an acidic pH. And salivary amylase, this is from your saliva, it has a neutral pH. Whereas arginase, which is in your small intestine, has high activity at a basic pH. All 3 of these are sensitive to pH change. As you can see, pepsin does not work past 4.5. Then you have salivary that doesn't work below 4.5 or work over, looks like 9.5. Arginase doesn't work at all below 5. That's because they're all sensitive. So most likely all of these enzymes denature, and if the enzyme is denaturing and changing shape, that means that the active site is also changing, which means that this enzyme cannot do the job. Please make sure you go over these notes and please study them for the exam. Uh-oh, I can't get this off. All right, ladies and gentlemen, give me a sec.